Hello everyone, my name is Phuc Nguyen. Today I'm excited to present our work OpenVO, Open World Visual Odometry with Temporal Dynamic Awareness. Given any uncalibrated dashcam video, OpenVO generates a real-world scale ego motion trajectory. It enables both low-level control using perception and high-level reasoning such as driving VQA and vision language action models. This bridges visual input into the actionable understanding in open world driving scenarios. OpenVO achieves matrix consistent camera poses and outperforms prior state-of-the-art method on KITTI, new scenes, and Argovers 2 by up to 20% overall and up to 92% in under sparse observations. Unlike existing approaches, it requires no ground truth alignment or bundle adjustment, enabling efficient and real-time deployment. This demonstrates that learning-based approaches can surpass traditional pipelines, state-of-the-art two-frame pose regressors without the additional modalities, even in open-world settings. We introduced two core components in OpenVO: time-aware flow encoder and geometry-aware context encoder. Given a pair of RGB dashcam frames, we estimate the metric depth from the metric 3D V2 and camera intrinsics from the wild camera to build a geometry-guided representation of the scene. To enable camera-aware representation, we tokenize a camera intrinsic into the normalized intrinsic field, describing the direction of the 3D viewing ray passing through the pixel in camera coordinate system. We further tokenize the first depth map by projecting each pixel onto its corresponding 3D point relatively to the camera origin. The intrinsic ray field captures the geometric projection pattern across the image plane. For example, pixels near the optical center correspond to the narrow ray cones, while those on the periphery represent the wider projection angles. The tokenized depth map results in the spatial distribution, effectively reconstructs the scene structure up to the metric scale, capturing both the directionality and the magnitude of each visual ray. Finally, these tokens are then assembled and then processed by a geometry-aware context encoder composed of a stack of 8 self-attention layers, which learn to correlate the intrinsic and the depth prior with the surrounding visual context. This produces a unified geometric embedding that generalizes across the uncalibrated dashcam and provides a consistent metric scale prior for world coordinate ego motion estimation. For time-aware flow encoder, we employ a pre-trained mass flow net encoder to extract pixel displacement field from a pair of image frames. From its intermediate layer, we obtain both the displacement map representing the horizontal and vertical displacement and the correlation feature which encodes the dense 2D correspondences between the two images. To incorporate the temporal information into the flow feature, we extract the frame rate from the video and map it to the time gap representation. This time interval is then expanded to high-dimensional embedding using the sinusoidal Pulsional encoding. This Pulsional encoding injects the smooth periodic variation of different frequencies that capture both fine-grained and coarse temporal scales, allowing the network to perceive and generalize across different observation rates. We designed two lightweight conditioning layers that take the encoded high-frequency representation of time to modulate the flow feature. Then, we convert the 2D optical flow and the per pixel metric depth into the dense 3D motion field using a fully differentiable wrapping mechanisms. This yields a metric 3D motion field aligned with the camera 1 coordinate system, tightly coupling for the 2D flow and a monocular depth while remaining end-to-end trainable. The adaptive flow feature for the 3D full motion field are then processed by the 4 self-attention blocks each. These attention layers refine the spatial correlation of each pixels, now enriched with temporal cues injected by the time conditioning layer. This enables the network to reason about the motion structures, the geometric relationship that are consistent with the underlying temporal dynamics, yielding the time-aware flow representation that are most robust to varying observation frequencies. To estimate the work coordinate ego motion, we concatenate the time-aware flow feature and a geometry-aware context feature, which is then mapped to ego translation and rotation by two MLP branches. Since OpenVO is explicitly conditioned on frame rate, we perform a temporal frequency augmentation during training to expose it to multiple timescales by subsampling the frames during training. We train OpenVO on the Singapore 1 North subset of new scenes and evaluate it on unseen regions of new scenes, as well as KITTI and Argovus 2 for cross-domain generalization and obtain state-of-the-art results after 96 GPU hours. Compared with recent works, OpenVO is significantly more robust to observation rates variations. We further investigate whether the network can implicitly capture the temporal dynamics and observe a notable performance drop on KITTI, while inconsistent motion pattern leads to the confusion. This highlights the importance of explicitly modeling the temporal structure for robust learning across multiple timescales. Here are some qualitative results on KITTI, new scenes, and Argovus 2. For new scenes. For Argovus 2. And we further bridge the gap to rework deployment by testing out method on in the wild dashcam video captured in Maryland College Park. And then we further integrate OpenVO into the vector map pipeline, allowing scalable and camera-only reconstruction of high-quality HD semantic maps reconstruction. And here are some of the cool results on scene semantic understanding using the blue ego motion predicted by OpenVO. To summarize, we propose OpenVO, a method that recovers metric consistent trajectories directly from uncalibrated dashcam videos. Our approach achieves state-of-the-art performance across KITTI, new scenes, and Argovus 2, with a consistent improvements across metric and strong robustness under sparse observation. Looking ahead, we believe extending OpenVO toward adaptive and fully end-to-end foundation model for autonomous driving is a promising direction. That's it. Thanks for listening.